Hey there and welcome. Today, we're going to move way beyond your everyday ruler to unlock a whole new level of accuracy. We're going to master two really clever tools that are the secret behind, well, pretty much everything, from a perfectly built engine to a delicate science experiment. We're talking about the Vernier caliper and the screw gauge. All right, here's the game plan. First, we'll talk about why this kind of precision is so dang important in the first place. Then, we'll take a deep dive into the Vernier caliper. After that, we'll meet its even more precise cousin, the screw gauge, and to wrap it all up, we'll learn how to deal with the tiny imperfections that every real-world instrument has.
So let's kick things off with a big question. Why do we even need these fancy tools? Well, it all comes down to needing to see things that are way beyond the limits of what our eyes and our regular rulers can handle.
I mean, think about it. Your standard ruler is perfectly fine for measuring in millimeters. But what if I ask you to measure the thickness of a single sheet of paper? Or maybe the diameter of a tiny wire? Yeah, for that, you're going to need a much smarter tool, one that can see all those tiny fractions that your ruler completely misses. And that brings us to our first key to precision, the Vernier caliper. So let's pull this thing apart and figure out exactly how this brilliant device actually works. The secret sauce to any precision instrument is something called its least count, or LC. You can think of it as the absolute smallest measurement it can possibly make accurately. And the Vernier's trick is that its least count comes from a tiny and very deliberate mismatch between its two scales, the main scale that doesn't move and the sliding Vernier scale. And here is that magic right in front of you. The divisions on that sliding Vernier scale are made just a little bit smaller on purpose than the ones on the main scale. That tiny, tiny difference between one main scale division, or MSD, and one Vernier scale division, VSD, that is our least count. This clever little mismatch basically acts like a mechanical magnifying glass, letting us see those tiny fractions of a millimeter. So how do you actually use it? It's really just a simple three-step process. First, you get your main scale reading. That's the mark just to the left of the zero on the sliding part. Second, you look really closely along that sliding Vernier scale and find the one single line that lines up perfectly with a line on the main scale. And third, you just plug everything into the formula. The main reading plus the aligning Vernier number times the least count. Okay, let's walk through this one together. First off, look at where the zero on the sliding scale is. It's just past the 10.2 centimeter mark, right? So our main scale reading is 10.2. Next, we scan across the Vernier scale and, yep, the third line lines up perfectly. So now we do the math. We take our 10.2 and we add 3 times our least count of 0.01. And that gives us our final, really precise answer, 10.23 centimeters. Now, the Vernier is fantastic, but sometimes you need to measure things that are even smaller. So let's level up our precision and check out the screw gauge. The screw gauge, which you might also hear called a micrometer, uses a really simple and reliable idea: a screw. When you turn that circular part, the thimble, one full 360-degree rotation, the screw inside moves forward a very precise, very fixed distance. And we call that distance the pitch. And that idea of pitch leads us right to the least count. Think about it. If one full turn moves the screw forward by one pitch, what happens if we only turn it by one single little mark on that circular scale? Well, that tiny bit of movement is our LC. And the formula is just beautiful in its simplicity. You just take the pitch and divide it by how many marks there are on the circular scale. Let's try to read one of these together. The main scale on the sleeve there shows a full 14 millimeters. Now we look at the rotating circular scale and we can see the 21st line is lined up perfectly with that center line. So with a least count of 0.02 millimeters, our calculation is 14 plus 21 times 0.02. That gives us 0.42. So our final diameter is 14.42 millimeters. See, not so bad. Okay, now that we've got the methods down for a perfect world, it's time to deal with a real-world problem. Because here's the thing, no instrument is ever perfect. And that brings us to the super important idea of zero error. So what is zero error anyway? Well, you can think of it as a mechanical mistake that's built right into the tool. It's what happens when you close the jaws of the caliper or the screw gauge all the way, and instead of reading zero like it should, it shows a small positive or negative number. To get a truly accurate measurement, you absolutely have to find this error and correct for it. Spotting this error on a Vernier is actually pretty easy. You just close the jaws completely. If the Vernier's zero mark is a little bit to the right of the main scale zero, that's a positive zero error. If it's to the left, then you've got yourself a negative zero error. And this leads us to the final, complete master formula for using a Vernier caliper. You take your reading just like we did before, but then, as the very last step, you subtract the zero error. Oh, and here's a pro tip. If you have to subtract a negative error, that's the same as just adding its positive value. The screw gauge has its own version of this, of course. If the zero on the circular scale is below the main reference line when the gauge is closed, that's a positive error. If, like in that second picture, the zero is above the reference line, well, that's a negative error. And so, here it is, the master formula for the screw gauge. The logic is exactly the same. You find your main scale reading, add the circular scale reading times the least count, and then, at the end, you subtract whatever zero error that particular instrument has. All right, time to put it all together in our final challenge. We've got a steel ball. The MSR is 0.5 centimeters. The 25th circular division lines up. The least count is 0.001 centimeters. So our initial reading is 0.5 plus 25 times 0.001, which gives us 0.525. But wait, we're not done. There's a negative zero error of minus 0.004. So we take our reading of 0.525 and we subtract negative 0.004. And remember, subtracting a negative is the same as adding. That gives us our final true diameter, 0.529 centimeters. So let's just do a quick recap of what we've learned. The Vernier works its magic using the difference between two straight linear scales. The screw gauge, on the other hand, uses screw rotation. And that fundamental difference in how they're built is why the screw gauge typically has a much smaller least count. It's usually about 10 times more precise than your standard Vernier caliper. So there you have it. You've now got the key to a whole new level of precision. I'll leave you with a final thought to chew on. Where do you see this kind of incredible accuracy at work in the world around you? In your phone? In massive bridges? What about life-saving medical tools? Where does this really matter most? Thanks for joining me today.